This is the final part of the cosmology section of the astrophysics unit, and as you can see on the screen, it's all about how we detect exoplanets. Now, an exoplanet is a planet that orbits a star outside of our solar system, and this has been of great interest in recent years in terms of finding somewhere that is possible for the human race to live on once we have ravaged the resources of this planet. And so what we're looking for is a planet which has water, and therefore we can get oxygen, extract oxygen from the water, and is the right temperature for human survival. And if you download the apps from any app store, either on the iPhone or Android, you'll see that exoplanets are discovered every day, probably on average 2 every day. So, but the methods of observing exoplanets are getting better and better, and as they get better, we discover more and more. So a little bit of history in terms of exoplanets. First one discovered in 1992, and the first one we discovered orbiting a main sequence star was in 1995. And we've, as I said at the beginning, discovered a lot more since then. Now, we have tried to observe them directly, so using telescopes to observe them, and the way we see the moon is because it reflects the light off the sun. So we're trying to, if we want to observe these directly, we're looking at how much light they reflect from the star they are orbiting, and that can be very, very faint, and it's very difficult to pick out the exoplanet. It can be lost in the glare of the actual star that it is orbiting. So the way we do it, so it's very difficult to observe them directly. So therefore, we have to use indirect methods, basically looking at the effects that the exoplanet has on the star itself. And these effects can be very, very small. And so it still is difficult to observe them, but the fact that we have launched a new telescope, the Kepler telescope, into space makes it has made that process a lot more reliable. So the first method we're going to look at is the transit method, and this is now the dominant method for detecting exoplanets. And as I said, the Kepler telescope, launched in 2014 with its main purpose being detecting exoplanets, has made detection a lot more reliable. And what you can see on the graph is the transit of an exoplanet across the star, and how its luminosity, the luminosity of the star changes, I should say. So you can see the orangey star, and a black dot moves across, which is representing the exoplanet. And as the exoplanet transits the star, we see a decrease in intensity. And from these measurements, we can actually work out quite a lot. And we're going to talk about the sort of things we can work out on the next stage. So in terms of bringing a bit of maths into this, we're going to assume that as we observe the star, it's a circle, and the exoplanet is also a circle as we observe them. And the area of the star is pi r squared, because it's a circle, and the area of the exoplanet is pi r squared as well. So what we're going to assume is that the drop in intensity, or the drop in brightness, is proportional to the radius So what we can say is that if we look at our expression here, this is the area of the planet, and this is the area of the star, so pi r squared, which is the radius of the planet, and you've got the radius of the star here. The pi's cancel, and then we can simplify our expression to radius of the planet divided by radius of the star squared. So this is the first bit of theory that you will need. So I want you to pause the video and have a go at these two questions which cover the content that I've just talked about. And when you have had a go at them, just continue with the video, and the next slide that you will see are the answers to these two questions. So it should take you about 10 minutes. Pause the video here and then continue for the answers to these two questions. So here are the solutions for those two questions. Question 19. The exoplanet, if it's very small and the star is very big, the reduction in brightness will be very, very small, and we need accurate equipment to measure it, which the Kepler telescope has helped us with. But the smaller the exoplanet compared to the star, the more difficult those measurements are. And also, we don't know when the exoplanet is going to transit the star. If we don't know anything about it, we could observe this star, and we could be waiting years for a transition to happen, or it might not even happen at all. So they are the two main difficulties with using the transit method. And then number 20A is using this idea of the relationship between the radius of the star and the radius of the exoplanet. So if we know the radius of the star, we can then work out the radius of the exoplanet. So quite a lot of useful information can be gained using the transit method. And here's another worked example for you to have a look at. So we're measuring the light from a star, and the exoplanet makes its transit here. First question is to work out how long it takes. So you're just looking for the time between those 2 points, which using the scale on the x-axis comes out about 5 hours. And then the exoplanet comes around quite quickly. So the period is the time it takes to orbit the star once, and it's the time between these 2 points, because it's obviously making another transit here. So it must have done one complete orbit, and quite a small period, 2.25 days, using the scale on the graph. And then just a straightforward one, measuring the drop in intensity. So you just use the scale of the graph and convert it to a percentage, which is 0.7%. So this gives you an idea of the type of question you might get looking at the transit method. Now, the next method of detecting exoplanets is called the radial velocity method. And I'm just going to talk you through the diagrams going from left to right. And you can see here that here's our star, here's our planet, and the grey circle represents the centre of mass. So the exoplanet will obviously be orbiting the star, but the star will also orbit around the centre of mass. So if we look at that, what the combined effect of these two is, their centre of mass is this point here, and they will both orbit around that point. So what that means is, if we observe the star and it's orbiting around the centre of mass, when we observe the light from Earth, so here's the light from the star coming to Earth, and the star is moving away from us, it will the light from the star will exhibit a redshift. So if you compare these spectral lines to these spectral lines, they've all been shifted to the red end of the spectrum. So if we look at these two spectral lines here, they have moved over more into the red side, and this has completely shifted off the spectrum. Now, when the star is in this position, there will be no red shift, but then when the star starts to come back towards us, when we observe that light, it will demonstrate a blue shift. So this change in we can then work out the change in velocity. So we can work out the speed of the star around its center of mass. If we work that out, we can then work out a lot about the exoplanet. So quite a power. So we're not actually making direct measurements of the exoplanet itself. We're making measurements of the star. So this slide is showing what we can actually calculate. Now, if we assume that the star is rotating around its center of mass, so here's the center of mass, here's the star, here's the exoplanet. As the star orbits the center of mass, rotates around the center of mass, because it exhibits a red shift and then a blue shift, we can work out the velocity of the star, so that's 0.1. We can then work out the radius of the star just by using speed equals distance over time, and distance is 2 pi r, which is the circumference of a circle. Using a bit of theory that we've not covered yet, we can use Kepler's law to work out the distance between the planet and the star, and then we can work out the mass of the planet. And if we then needed to, we can work out the density, and that's useful if we compared the density of that planet to ours. So quite a lot of information, as I said, we can gain by observing the indirect effect of the exoplanet on the star that it orbits. So quite an interesting area of physics, and covering quite a lot of physics from different areas. So what I want you to do now is to this is the end of the video, so I want you to have a look at the attached questions that are in the assignment, and they are all about applying this theory that we've looked at today in terms of detection of exoplanets. And when you have done those, if you can submit those back to me, I will have a look at your answers. So thank you.